So for this problem, we have a Stefan tube with acetone and methanol originally in the liquid phase. At the top of the tube, there's a screen where air is blowing across at a high velocity. At the liquid interface, Z is equal to 0, and at the top of the screen, Z is equal to delta. Component 1 is acetone and component 2 is methanol. We want to solve for the molar fluxes of acetone and methanol in this situation, and we are given initial conditions for the mole fractions of both of these substances. We are also told that delta is equal to 0.24 meters and are also given the pressure and temperature within the Stefan tube. Finally, we are given the Maxwell-Stefan diffusion coefficients for the situation. Since we are given these diffusion coefficients, we can solve for the molar fluxes of acetone and methanol through Maxwell-Stefan relationships. So we can write out the Maxwell-Stefan relations for components 1 and 2. So we get the change in mole fraction of component 1 with respect to Z is equal to the mole fraction of component 1 times the molar flux of component 2 minus mole fraction of 2 times the molar flux of 1, all over the concentration times the Maxwell-Stefan coefficient, plus the mole fraction of component 1 times molar flux of 3 minus mole fraction of 3 times molar flux of 1, all over the concentration times D13. We can write our second relationship for the change in mole fraction of component 2 with respect to Z. So we get Y2 times N1 minus Y1 times N2 all over concentration times Maxwell-Stefan coefficient, or it should be D12, yes, plus Y2 N3 minus Y3 N2 all over concentration times D23. So in this situation, the mole flux of component 3 can be assumed to be 0 because air is not diffusing down into the liquid in this situation, so its molar flux is equal to 0. So this simplifies our equations just a little bit. Now, we can see that these are simultaneous ordinary differential equations, and we have initial conditions, so this can be solved as an initial value problem. And we can do this in an ordinary differential equation solver, but in order to do this, we need initial guesses for the molar fluxes. So in order to do this, we don't want to just guess a random number because then the values may never converge and we may never get an accurate solution. So we want to do an order of magnitude estimate for these molar fluxes just so we can get a little bit close to the actual value. So we can first do this by scaling this situation. So we have Z is equal to 0 at the interface and Z equals delta at the top of the screen. So we want to define a new term eta, which is equal to Z over delta. By doing this, we get any point eta, which eta would be a dimensionless number in this case, because both Z and delta are in terms of meters, so if you divide the two quantities, you get a dimensionless number. So at any point in this vapor phase is a number between 0 and 1. So by dividing by the total length, you scale this quantity down to 1, and that makes everything just a little bit easier to solve. So we want to rewrite this first equation in terms of eta. So we get the change in Y1 with respect to Z is equal to the change in Y1 with respect to eta times the change in eta over the change in Z. So this is the same thing right here, just written, trying to get everything in terms of eta. So we know eta is equal to Z over delta, and this right here is just the derivative of eta. So with respect to Z, the derivative of eta is 1 over delta, and we want to multiply this by the change in y1 with respect to eta to get both sides of this equation to be the same. So we get 1 over delta times dy1 over d eta is equal to the change in y1 with respect to z. So we can then rewrite this equation right here to get the first equation in terms of eta. So just rewriting this equation really quick. And since this molar flux of 3 is equal to 0, we can just get rid of that term entirely. So we need to pay close attention to the negative signs right there. Oh, and we can also rewrite y3 as 1 minus y1 minus y2, since the mole fractions of the components must add up to 1. And we can multiply each side by delta. So right here we have the change in y1 with respect to eta is equal to this right side of the equation, which was multiplied by delta. So we know that y1 is any quantity from 0 to 1, so the order of magnitude of this must be 1, and then the order of magnitude of eta is also a quantity from 0 to 1. So the whole order of magnitude of this side of the equation must be equal to 1. Over here, we do not know the order of magnitudes of each component, but we know that these must be approximately equal since they have the same molar fluxes and mole fractions. And then we know that this term of the equation must be equal to the order of magnitude on this side, so this whole thing must be order of magnitude 1. We already know that delta and the mole fractions already have an order of magnitude 1, so the molar fluxes divided by the concentration times the Stefan-Maxwell diffusion coefficient must be equal to order of magnitude 1. So what we want to determine is the order of magnitude of the molar fluxes, and we know what we can solve for concentration, and we already know the Stefan-Maxwell coefficient, so we can determine the order of magnitude on the bottom, and the order of magnitude on the bottom of this term must be equal to the molar fluxes, must be equal to the order of magnitude of the molar fluxes, since they must be equal to 1. So concentration is equal to pressure over the ideal gas constant times temperature, and then times the Stefan-Maxwell constant. So we know the pressure has an order of magnitude of 10 to the 5th in pascals, since this has 2, and then we want this in pascals, so it's order of magnitude 10 to the 5th. And then the ideal gas constant we know is about 8, so we know that this is an order of magnitude of about 10. And then temperature is 325, so that's an order of magnitude of 100. And the Stefan-Maxwell constant for a gas has to be 10 to the negative 5th meters squared per second. So we know this order of magnitude. So these cancel out right here, and we get the order of magnitude of the the order of magnitude of the denominator must be equal to 1 over 1,000, which is equal to 10 to the negative 3rd. So then we know that the molar fluxes of component 1 and component 2 must also be approximately 10 to the negative 3rd. We want to use these as our initial guesses when we solve these simultaneous differential equations in Python, so we can use these order of magnitude estimates as our initial guesses.